Have you noticed how electrical power lines along the highway hang loosely on a hot afternoon, but look pulled tight on a chilly morning? To understand why this happens, imagine you and a group of friends are standing shoulder to shoulder in a tight circle, with your arms securely linked together. If everyone in that circle suddenly starts jumping up and down with a lot of energy, you can't stay right next to each other. You have to take a step back to keep from bumping elbows. As everyone backs up, the entire circle naturally grows larger. We naturally need more physical space when we're moving with high energy. It turns out every physical material in the world behaves the exact same way when it heats up. Everything you can touch and see is built out of microscopic pieces called particles, and they are constantly in a subtle motion. When an object gets hot, those tiny particles gain extra energy. They start to vibrate rapidly, shaking and pushing their neighbors further apart. Now, it's easy to assume the individual particles themselves swell up like tiny balloons, but they aren't changing size at all. The object grows simply because the empty, invisible space between the particles is increasing. We call this outward growth expansion. When the object cools down, the exact opposite happens. The particles lose energy, slow their shaking, and pull closer together, which shrinks the entire object. We call that contraction. So we have a universal rule. Adding heat makes particles move faster, creating expansion. Removing heat slows them down, creating contraction. This rule applies directly to massive construction projects right here in Uganda. Look at this wide aerial view of the source of the Nile Bridge. Solids like steel and concrete actually expand the least out of all materials because their particles are tightly locked together. But across miles of bridge, millions of tiny outward pushes add up to an immense amount of physical force. If the midday sun heats up that rigid concrete and metal without giving it any extra room to grow, the overwhelming pressure will cause the entire structure to buckle and break. To prevent this, engineers build deliberate gaps into the structure. This schematic shows an expansion joint. As the temperature rises, it gives the expanding metal an empty space to safely slide into. We cannot stop solid particles from pushing apart when they get hot, so our bridges and railways must be built to accommodate them. If solids expand just a little, gases are on the opposite end of the spectrum. Gases expand the most out of any material because their particles are not locked together. They are completely free to roam. You can see this for yourself by stretching a deflated balloon over the mouth of an empty plastic water bottle and sitting that bottle in a basin of hot water. The heat from the water transfers through the plastic and energizes the trapped air. Those gas particles begin to race frantically, pushing outward in all directions until they stretch the balloon. This is the same reason hot air balloons fly. As the flame heats the air, the particles spread out to fill the giant balloon. Because the same amount of air is now taking up much more space, it becomes lighter than the cool air outside. And just like a tiny bubble in water, that lighter air floats upward, lifting the whole basket with it. This comparison chart shows how much different materials grow under the exact same heat. Solids barely change, liquids expand a bit more, and gases swell dramatically. How much an object grows simply depends on how much freedom its particles had to begin with. So far, we've established a rule that governs our environment. Materials expand when heated, and they shrink and contract when they cool down toward freezing. But you might have experienced a household mystery. Have you ever put a completely sealed glass bottle of water into the freezer to chill down quickly, and then accidentally forgotten about it? When you open the freezer the next morning, the bottle doesn't contain a smaller, shrunken block of ice. Instead, the solid glass is shattered into pieces. This happens because water has a very strange habit. While almost every other liquid in the universe shrinks as it gets colder, water stops shrinking right before it freezes and starts growing larger instead. Water is the universe's great rebel, refusing to follow the normal rules of contraction as it turns to ice. To see why this backward behavior is so crucial, look at this deep crater lake. Imagine what happens to the water here during a severe freezing winter. This cross-section shows the cooling process. As the lake drops to exactly 4 degrees Celsius, the water behaves normally. It shrinks down to its heaviest state and sinks straight to the bottom, where the fish are swimming. But as the water gets even colder, dropping from 4 degrees down to 0, that weird exception kicks in. The freezing water suddenly begins to expand. It becomes lighter, rising right back up toward the surface. Finally, at 0 degrees, the water turns into solid ice. It grows so much that it is forced to float right on top of the liquid water, forming a distinct barrier over the lake. That floating ice acts just like a thick, insulating blanket. It keeps the heavy 4-degree water resting at the bottom warm enough for fish and aquatic plants to comfortably survive the long winter. The invisible push and pull of particles dictates the physical world. It dictates how we engineer a safe bridge in the hot sun, and it provides the exact quirk of nature